Hey guys, this is lesson 8.2 and we're going to be talking about concavity and points of inflection, which all have to do with the second derivative. So let's get started. Which function that you see right in front of you do you think is actually increasing? So remember from the last video we had said that increasing means that your slopes or your derivative is positive. So let's take a look at the slopes. Starting at f at x, this slope is positive, 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 positive. Since they're all positive, it looks like from left to right, you're increasing. Okay, so f at x is an increasing function. Going on to the g at x, also increasing, and increasing and increasing. Okay, so all of this from left to right is also positive function, positive slopes and an increasing function. But it seems like, obviously she's talking, she wants to make a point about something. They look kind of different, don't they? Like, how can they both be increasing, but they have different shapes? Well, that's because f at x is something that we call concave down, whereas g at x is something that we call concave up. And so concave down and concave up are defined below, but basically f at x is an example of concave down, where you see like the tangent lines are lying on top of the graph. So that's a general definition for concave down, whereas concave up, as you see in g at x, is where all the tangent lines are lying right below the function itself. Okay, so we're going to get into more specifics in a little bit. Now that we know the definition, why don't we kind of consider this function now? So where in this crazy function do we see concave down and concave up? So let's do concave down first. That's going to be wherever I can draw tangents above the graph itself. So this is above the graph, this is above the graph, and all of these lines that I'm drawing are on top of the function itself, up to maybe about here. We've done this before, but maybe we haven't really looked at it or paid attention to it. Do you notice that all of a sudden, somewhere in the middle, you kind of start switching from like above the graph to below the graph, and we start like drawing these lines underneath the function itself up until about here, and then we switch back again above the graph, and then we switch again to drawing them below the graph. So you see, you can kind of take a look and see where my concavity changes from a concave down to a concave up and a concave up to a concave down. Now, when it changes from one place to another, then that means we have something called a point of inflection. So the first dot that I put down was a change from the blue, which is our concave down, to the coral, which is a concave up. And then this point of inflection is from a concave up to a concave down. And so there's one more, which is right here. Each of these are called POIs. So I know we use POIs as points of intersection, so just know that they could mean either. Okay, but they're basically when your concavity changes. So keep that in mind. Again, we're going to use it later. Taking a look at this graph now, which we call f at x, you should know, kind of, now that you're a little bit familiar with it, that this is a concave down. So notice that we have slopes that are on top of the graph, so this is a concave down. And that must mean that, we can take a look at the slopes too. Each of the slopes is negative, but when we take a look at the negativeness of each one, compare them to each other. Like this one has a slope, and like we said, it's negative, so the first derivative is negative. But that first slope is actually really flat. And so I'm going to say that it's probably like 0.0 small numbers, okay? Anyways, this one is probably going to be a little bit more steep. So maybe -1/2, we'll just say. The next one we can say is maybe -2. And then now we're getting even steeper. Maybe -5. So when we compare all of the slopes, that's what the second derivative means. It's a comparison of the first derivatives. Remember, slope is first derivative. right? So when we compare them, we're saying, oh, they're actually decreasing because negative 1 over 10 is a lot smaller than negative 5. So it's increasing in the negative direction, which means it's decreasing. When your second derivative is a negative number, it means that you're going to have a concave down. So here is the overall rule. When your derivative, your second derivative, is less than 0, which is a negative, you're going to get a concave down, which is this type of shape. When it's a positive, you'll get this type of shape, which is a concave up. Now, when it's exactly 0, then that means that you're changing from concavity to concavity, from either concave down to concave up, or concave up to concave down. And you can calculate that by setting the second derivative equals to 0. So let's do a full analysis together, like an entire question, and then I'll run through a couple questions with you. Determine the intervals of concavity for this original function, and also include any of the points of inflection. So already when I see this type of question and I notice they say concavity, I'm like immediately second derivative is in my head. Okay, so number 1, first thing I have to do is I have to find, actually, you know what? I'm going to color coordinate this the way that I always have. I need to find the second derivative, which I usually use this color, f double prime of x. All right, which means that we're going to have to run through each and every one of the steps. You need your original, right? You need your first derivative. I'm just doing power rule. And then you also need your second derivative. Nope. 48. Because I can multiply. There we go. Okay, so that was the second derivative, and that was pretty easy. Now I need to test for certain intervals of concavity. In order to find those, what I want to do first is I need to find those points of inflection, because when I get the points of inflection, I would be able to create the domains, the regions for my intervals of concavity. So number 2, what you want to do is you want to set your second derivative to 0. Okay, so you have 12x squared minus 48x equals to 0, and since we have two x's, it's probably a good idea to factor. So solving this one, I'm going to get an x value of 0, and solving this one, I'm going to get an x value of 4. So both of those are x values for my points of inflection, which I'll do a little bit later. Let's work on just the intervals of concavity for now. Okay, so number 3, we're going to get concavity intervals. All right. So since these are the important numbers, I'm going to go from negative infinity to 0, 0 to 4, and 4 to infinity. I don't want to include the 0 and 4 in my intervals because that's when it equals to 0, and we want to test when it's greater than or less than 0. All right, and what we're testing for is our second derivative, because this is a second derivative test, and that's going to tell us what our function actually looks like our overall function. Okay, so when I sub in the numbers into my second derivative, I get a positive here, a negative, and a positive. Now, what does that actually mean about my original function? So when your second derivative is a positive, you're going to get a concave up. So over here, you also have concave up. Now, when you have a negative, it's going to be concave down. So overall, you should expect, and I'll move this in a second, that your graph will have this general shape to it. All right, I'm going to put that back. So like we said, you have points of inflection here, POI, at x is 0, and also a POI here as well. Okay, so maybe we should figure out what those are, but you know what? I should probably write down as a therefore what my concavity is. So therefore, it's going to be concave up from x at negative infinity to 0 and from 4 to infinity, and then concave down for the domain of 0 to 4. All right, so that's a check mark for the very first question because they asked us for the intervals of concavity, which is what we gave. And they also asked us to include the points of inflection. So we want to make sure that we figure out what is f at 0 and what is f at 4. Okay, so I'm getting a 0 and I think that was negative 256. And so you're going to get POIs at 0, 0, and 4 and negative 256. Okay, so the overall rule, and what we already talked about, is that you get a concave down at a specific critical point. Okay, so in the last example, our critical points were 0 and 4. And if it's a concave down, notice that you get a maximum, right? When you have a concave up, notice that you get a minimum. So we have an overall rule. This is called the second derivative test. And so when we do our first derivative, okay, so any of our first derivatives first, and then we take a look at our second derivatives, which are going to be either concave down or concave up. Okay, we're going to get local maxes and mins. All right, so just like what the previous slide had said at the bottom, you're going to get a local max when you have a concave down, obviously. You're going to get a min when you have a concave up. Okay, now if you have both like your first derivative and your second derivative as 0, then you're going to go back to like doing a little bit more testing. Okay, so you're probably going to want to test using an interval, so at a critical number, if you're going up and maybe up again, like increasing and increasing. So this is just my very quick interval table. You're going to basically have to do more testing to see what's happening there if you don't have a maximum or a minimum. You might have, say, I don't know, like no turning points. Or it could be, I mean, like it has to exist because if it doesn't exist, this actually doesn't apply. So an example of when it doesn't exist is when you're talking about an asymptote. Okay, so let's scroll through example number 2. Determine the local extrema. So as soon as they say that, I think derivative, like first derivative. Okay, and points of inflection. So obviously they're talking about second derivative. All right, so number 1 says find my first derivative. Taking my original, going through the purple, I find my very first derivative function. To find the local extrema, then we have to set the first derivative equal to 0. And we're going to solve for the numerator, any x values, because those are going to be critical numbers that I'd probably put into an interval table. Also considering that any of the vertical asymptotes are also critical numbers that would go into my interval table. Okay, so points of inflection. Actually, you know what? Let's go into this a little bit farther. So what is this? Is that going to be, I mean, like I know that it's a specific critical number. That means when we test for something like this, we're finding out, is it a max? Is it a min? I don't know. But I know that some sort of peak is happening there, and that's why the slope is 0. So we do something called a second derivative test to figure out if it's a max or a min. So we can sub in our critical number into the second derivative after we find the second derivative and check out what we get. And if it's positive, then we know that it's a concave up, just like the rule said above in the box. If we want to know exactly what that point is, well, we can sub it into the original function and we get our point right here. Okay, so that point is going to give us a concave up. So this is where the point is. That would be the -1 and 3. And it would be a local minimum because it's a concave up. Now finding points of inflection, you're going to have to take the second derivative, set it equal to 0, and again solve. So at this point, once you've simplified everything, that's what the numerator is going to be for, looking for any x values that will help us find our POIs. So I found like an x value of the cubed root of 2. So if I wanted to figure out exactly what that POI is, I'm probably going to have to substitute this back into the original formula. So I'm wondering actually if I wrote this down incorrectly. Maybe, probably. That this probably should have been f at x. Okay, so we get our point of inflection at cubed root of 2 and 0. Now that would have been an important point to put into, say, an interval table, if I needed to explore further with any vertical asymptotes as well. So this number is also a critical number that I'd want to put into an interval chart if I wanted to see what the graph looked like. But that's not exactly what this question asked for, so I'm not going to go any further. All right. So here's a question that's a little bit tricky. Sketch the graph of a continuous function, and it has to satisfy those 4 pieces of information. So let's start to dissect this. What are they asking us for? Looks like a concave down from 0 to 2. Okay, so 0 to 2 is a concave down. That's like this type of shape. So I guess they didn't really tell us anything else. I guess I can just, ta-da, right? Sort of crooked, but that's okay. All right. They also told us it's concave up from 2 to infinity. 2 to infinity. So something like this. Continuing. This one's probably continuing. Okay. They also said that they wanted a specific point at 1 and 0. Well, rather, at 1, you're going to get your peak, which has a slope of 0. Okay, so that's what this guy's saying. You have a slope of 0 at 1. You also have a slope of 0 at 3.5. I did not draw that right then. So why don't we get rid of this guy? We'll redraw it. And at 3.5, we'll get some sort of a peak. So something like that. Okay, so that's 3.5 right there. So I'm going to have my peak right here. And that's it. It doesn't matter how high or low the peaks are because they didn't give us that information. So we did satisfy all 4 of the characteristics. Now, let's throw some trig in there because why not? Example number 4, determine the intervals of concavity and points of inflection for something with a trig function and it has a domain of 0 to 4 pi. Okay, so intervals of concavity and points of inflection, obviously second derivative. So I have my blue original function. I'm going to scroll down, I'm not going to go through all this. Okay, the purple is our derivative. I went all the way to the end and simplified it as much as I could because you want to make it simple so that you can take the second derivative. You don't want to have to take a second derivative of like this step. That'd be terrible. Okay, so I'm going to leave the first derivative right there in plain view. And then what I would do is do the quotient rule to do a second derivative. So I'm going to keep scrolling down. If you want to pause the video, definitely go ahead. So I'm going to go down to maybe here. All right. What I want to do now is I want to analyze the numerator and the denominator. Making this a 0 will help me find my points of inflection. So this guy right up here is what I'm going to analyze to figure out my x's. The denominator is going to be my vertical asymptotes. And so if I scroll down, let's talk about the vertical asymptotes first. So taking a cubed root, whoops, not there, here, cubed root is going to give me sine x can't equal to 0, because if it does, the denominator is going to equal to 0. And from a range of 0 to 4 pi, I mean, like, you can think about the graph, 4 pi is going to be 2 cycles, right? So there should be 1, 2, 3, 4, 5 answers, 1, 2, 3, 4, 5 answers where x can't equal to 0. So you actually have 5 vertical asymptotes. Now on the other side, you want to, okay, so here's some tips. In order to solve for 0 with any of the trig, try to get everything into one type of trig function. So whether it's sine or cos, just try to get them into one, because then you're only looking at one type of function at a time and makes it a lot easier to solve. So I converted my sine to a cos and just simplified it into a quadratic, and then I factored it. So as I factored, I mean, like, you see that they're both the same, so it doesn't really matter which one I'm talking about, but either one of them can equal to 0. And so cos of -1, I mean, let's take a look at the graph. Oh, sorry, we're supposed to do from 0 to 4 pi, right? -1 is going to happen twice. And so these guys are right here. So what exactly is the answer when we take our intervals of concavity? Should we include pi because we said we couldn't have it? Should we include 3 pi? Well, we said that we can't have that either. So x can't be those two numbers, which means that we actually have no critical numbers. So that's what this is saying right here. The asymptotes supersede, or they're more important than the zeros themselves. And so since we don't have any numbers here, we don't have any points of inflection. All of these numbers that you see, I put in teal so that you guys could see each of those are the asymptotes. So there should be asymptotes all along here, and even though some of those had ended up to be our critical numbers, they're actually not considered critical numbers. Again, because they can't be there, an asymptote is more important. And so even if you say that there's a critical number there, an asymptote will be like, you can't touch me. So putting in all of your numbers, we didn't take a look at the regions from -infinity to 0 or from 4 pi onwards, because we were only looking from 0 to 4 pi. So you'll notice that the original function is concave up from 0 to pi and from 2 pi to 3 pi. It's concave down from pi to 2 pi and 3 pi to 4 pi. And since there are only asymptotes, there will be no points of inflection. I'm going to make up a new word. I'm going to call it interflection, and yeah, that's what I'm going to name my child. Okay, interflection. Hey, interflection, come over here. That's what I'm going to say. Okay, so that's it for 8.2, and next, I believe 8.3 is about asymptotes. See you later, guys. Have a great day. Oh man, it's raining outside. Oh, I don't have an umbrella. See you later, guys.